Okay, all right, all right. Good morning, everyone. Today we have Shuvayan Brahmachary. Today he's going to be talking a little bit about LLM-based optimizers. So these are using LLMs to mimic evolutionary computation and evolutionary systems. And so the title is LLM-based optimizers, reasoning via. So please join me in welcoming Shuvayan.
Thank you, Professor Dozier, for the kind introduction and also inviting us to present our work in this community. It is a matter of honor for us to be able to share our work with the larger audience and get the message across. And in the meanwhile, get their feedback about the work that we're doing. So yeah, thanks a lot. Right, as Professor Dozier mentioned, this is a work which essentially uses large language model for optimization for problems that have certain practical relevance from the industrial settings. And I especially want to emphasize today on the reasoning via elitism part. This is something that I will be focusing on much later towards my presentation, towards the end. However, this is the central medium via which we are trying to convey why large language model as optimizers, or for that matter, any decision would actually be worth it, right? So yeah, to that extent, this is the premise of the work. Meanwhile, I'm a researcher here in the Shell Technology Center, Bangalore. I work for the molecular products discovery team, which earlier used to be the scientific machine learning team, right? But we have moved to a different team now. Uh, yeah. So before I begin, just as a cautionary note, this is going to be a presentation where we're going to discuss about future research. This should not be taken as a means for your investment into Shell. So yeah, just another cautionary note. Right. It is only fitting that I introduce my team to you. Uh, like I mentioned, now it is called the Products Discovery AI team, which is headed by Kaushik Kalyanaraman. And he manages multiple people. And as you can see, they wear multiple hats, which really allows us to take different kinds of projects, not necessarily only optimization, but something that requires us to develop models for that access neural surrogates for certain kind of an equipment or real, digital twins, something like that. Right. Uh, Now, as far as our team is concerned, our focus area are predominantly neural manufacturing system, climate transition technology, complex system technology. We specialize more especially in scientific machine learning as well as multimodal AI. There's a lot of uh, generative AI that comes into play as well. Now, as far as methods are concerned, we use physics-informed neural network, neural operators, graph machine learning, so on and so forth. Right. So that is the focus area. Now, at this point in time, you might be asking, what do I mean by neural manufacturing system? That's something that is one of our focus area, right? So now this, when you think of Shell, you probably think of a big energy industry, right? Which focuses on oil and gas. But in fact, in reality, Shell deals with multiple facets of energy, from solar, wind, geothermal, and of course, there is the oil-driven LNG based energy as well. Now, all these facets of energy deal with multiple components and multiple sectors from upstream to downstream. Now, you can think of there is exploration, there is extraction, uh, plant optimization, carbon capture, wind farm, satellite imagery as well. So there is a lot of work that goes behind the scenes when you think of Shell. So what we try to do as a team is that we are trying to build system level uh, surrogates. Let's say let's say heat exchanger, right? When you think of heat exchanger, you think of heat and mass balances. Now, what we are trying to do is use those governing equations and design neural surrogates which can inform us of the underlying physics, but at a fraction of a second, right? A fraction of the actual compute that is required by, let's say, traditional solvers. So that way, we are able to give you an informed decision much quicker. So that's the entire agenda behind our team existence. And doing so, we also have ventured towards different uh, problems. One such problem was the optimization using large language model. Now, that was a curiosity-driven exercise that we started in the month of uh, November in 2023. So that's when we realized that there is a lot of potential for a large language model. And then we saw that two interesting papers that were released by Google DeepMind as well as NVIDIA. So on your left, you can see the paper Large Language Model as Optimizers, which was released by Google DeepMind, where the emphasis is largely to solve combinatorial optimization problem, as well as to optimize the prompts that can give you an accurate answer. Now, our focus has been slightly different, and that got motivated by the second work that is on your right. This is Eureka, which was developed by researchers from NVIDIA. The central idea is, can we use large language models to train how a robotic arm can spin a pen around its fingers? Now, that's a control problem, which requires a lot of hit and trial. So how this worked is that you assign the control policy to the entire problem. So there is a large language model which decides the policy, and then it will then come up with the inputs which gets fed to the simulator. The simulator is the environment where this entire exercise is being computed. That is, the robotic arm picks the pen and it swivels the pen around its arm. Now, it might fail, it might succeed. So it, based on its action, is going to compute an outcome. That becomes a reward. So LLM then takes the reward after it has fed the input, and then the iterative process continues. So yeah, that was the work which motivated us to take this path. And we thought, okay, why not try how well a large language model can perform when it comes to complex optimization, not just single objective as well as multiple objective as well. So that led to us further investigating with the entire team, and we published a paper which got published in Neurocomputing. I also have to mention that this was done in collaboration with an external collaborator who is presently a professor here in Worcester Polytechnic Institute. Right. So feel free to have a look at this paper. I would be happy to answer your questions. If you have any, feel free to reach out to me as well. Okay. Now, that aside, now that we have set the context behind what prompted us to do this work, now let me also share the contents for today's presentation. I'm going to be talking a bit about the basics, motivating behind our framework, and then benchmark, what kind of benchmark algorithms we have tried, right? And finally, we'll come to the core of this work where we have applied it to multiple practical problems of interest. And we'll also talk about large language model reasoning. Right. I will take it for a fact that the audience today understands a bit of optimization. So I'm not going to go into great details. This was a slide that was meant for a generic audience, which is why I kept these informations available as well. So now, you might be aware when it comes to optimization and proving the merits of a new optimization methods, typically it is done via benchmark problems. Now, benchmark problems are of many, there are many examples. Rosenbrock is a simple example. And you can see in 2D, in 2 dimensions, the function is given by this equation right here, but it can be extended to n dimensions as well, right? So if you look at the value of the function with respect to these decision variables, which are inputs X and Y, this is what it's going to look like on your right. So you can see the global minima lies somewhere there, and you start with somewhere else because you do not know when you start a problem where is your optimal solution. You do not know that. You're trying to find that solution, right? So that becomes your initial guess. And based on whatever schema you choose, you iteratively converge towards the solution. Now, many a times it depends on the problem and also depends on the method you choose. Uh, you could choose gradient-based optimization, which may not perform as well for multimodal optimization problem. And that will become clear in the coming slides. All right. Okay, now let me also discuss with you the idea behind population-based approach. Now, as my Professor Doshi mentioned towards the beginning, this is an attempt to mimic a population-based approach using large language models. Now, what do I mean by population-based approach? It is an approach in simple terms when you begin by a population of solutions or multiple solutions as your initial guess. That is, let's say I'm trying to optimize for this problem here, which is in 2D, and I can see the ISO function lines. I can generate solutions randomly anywhere, and these are shown. And based on the initial solution, your optimization will take different trajectories. You can see here, right? These red points, the yellow points, these uh, take different trajectories and approach towards the solution. But only one of them has been able to identify the global optimal solution, which is indicated by the star. So that essentially what it means. That's the advantage of population-based approach, because with more number of solutions, you're exploring the entire design variable space, and you end up with the optimal solution. Right. I mentioned something about exploration and exploitation. It might be worthwhile to also understand what that is. I'm going to just take a few more seconds to explain that. Now, imagine you have a 2D design variable space, and you want to find the optimal solution, but you do not know where the optimal solution are. What you would do is explore the design variable space. That is, generate solutions so that you skim the entire design variable space. So you see they are randomly spread out everywhere, these solutions. On the contrary, exploitation means something opposite. That is, you will produce solutions or candidate solutions that are in close vicinity of each other. Now you might think, why would one do that? Because my uh, optimal solution may not lie there. Well, the idea behind exploitation is, as your optimization progresses, your optimizer might understand that there is a good region around this space, and I might want to exploit that region even more by populating more solutions. That's the idea. You do not know exactly where that is, but if I generate more solutions around that point, I might be able to do it. I might be able to find it. So that's the dichotomy between exploration and exploitation. All right, and we try to achieve this by introducing elitism as well. Now, elitism is also a key term that is introduced with optimization, specifically with population-based approach. Now, you might ask me, what is elitism, right? Well, let me show you with an example. Let's see, in the 2D design variable space, you know where you have this global optimal solution, but you do not know where it is. So you start with an initial guess in the explore pool and exploit pool. Same initial guess, right? And this is how it looks like at time t is equal to 0. Now at iteration 1, you generate new solutions on both the explore and exploit pool. And one of them appears to be closer. How will you know it's closer to the global optimal solution? You will definitely know its function value, right? Let's say it's Rosenbrock function. You can evaluate the f of x of y. then you will know that this solution right here is the lowest value. That way, you know it's closer to the global optimal solution. So what you may want to do is retain that solution definitely for the next iteration. You do not want to lose it. That's why we port the solution onto the exploit pool. And here, then the number of population becomes uh, 10 because we started with 8, we introduced 2 more, and that becomes 10. But we cannot let that happen. We have to maintain the same size. So we'll get rid of 2 bad solutions from the exploit pool so that the balance remains. And now that you have this set of new solution, we will then continue the process again and again. We'll generate more solution in the exploit pool and generate more solution in the exploit pool. All right. So that is basically the principle behind exploration and exploitation. Now, I had mentioned that we had done a lot of study for benchmarking, right? This method that we have devised, it has its merits has to be quantified, and this has to be done with respect to the state-of-the-art methods that exist out there. So for single object optimization, we went for stochastic gradient descent, ADAM, LBFJS, simulated annealing, CMAES, and COBILA as well. Now for multi-objective optimization, we compared our solution with NSGA2, which was back way back in the year 2002. Now it's a very popular method, and it's like 50,000 or plus citation. It's really good for multi-objective optimization. Right. But here's the thing. For multi-objective optimization, you don't necessarily have a single solution because you might be working with conflicting objectives. Let's say I want maximum oil production and I want minimum environmental impact. So those are conflicting objectives. In such a case, you do not get a single solution. You get a family of non-dominated solution, which gets referred to as the Pareto optimal front. You see these green marker points, these are my optimal points, which are referred to as the Pareto front. This is what the optimizer is striving to get. All right. Okay, so with that out of the way, the final slide for the motivation, and I'll promise I will get back to my framework, is the motivation. So you might ask, okay, there are tons of methods already. Why would you want to devise something new? Well, it's all good and fine when you're working with in a simple objective function that looks like this. Let's say the sphere function, right? You start anywhere, you're bound to get the optimal solution within a fraction of a second. However, things are not very trivial when you move to slightly more complicated problems. For instance, Rosenbrock function, there exists local as well as global optimal solution. The Himmelblau function, which happens to have multiple global optimal solution, and so on and so forth. So yes, the idea was to see how well this large language model based evolution optimizer, or LEO, like the way we call it, performs on these set of problems. Okay, so here's my framework that we have devised. Essentially, as I mentioned, you must have guessed by now, this requires some form of large language model. So we have used Llama 3.170 billion as well as ChatGPT 3.5. Both of them were used. You design a prompt, say that you are an intelligent assistant who can understand great technical details. You'll help me with minimizing proof functions by taking cues from the given information. So that's the prompt that you feed to the large language model. The large language model processes that information with the additional information of the candidate solution. It then tells you the next set of new solution to generate, and then you enforce guardrails and the process continues. So that's the overall process. But to take you one level deeper, let me also explain process with this framework. We start with an initial guess, initially randomly generated guess. So on your left, you can see the blue markers. Those are my initial guess. Let's say this is the Himmelblau function, where my global solutions are 4, and those are represented using stars. And my initial guess are not very great. They are far off from all the optimal solution. And this is your exploit pool. And on your right, we have the explore pool. So initial guess is same for both of them. Now, what you want to do is you want to evaluate the goodness or the fitness of these values or these solutions. By that, I mean you evaluate the function values. So you can do that easily. Just use your function evaluator to compute the function values for all the solutions. Let's say there are 10. So you'll get 10 scalar values for both exploit pool and explore pool. Now, this is where large language model comes into the picture. You ask large language model, these are my initial guess, and these are the associated function values. And based on where you are, whether you are at the explore pool or the exploit pool, you then change your prompt. You ask, let's say you are in the exploit pool, you ask the large language model, so these are my initial guess, and these are my function values. Suggest me new set of solutions within bounds, bounds, whatever the bounds they are, such that in the next iteration, my function value is going to be lower. And these solutions has to be generated so that they are spread around. So you see, there are 2 criteria it has to satisfy. It has to satisfy exploration, and it has to satisfy one more criteria such that you generate these solutions such that the function value in the next iteration is lower. So that's the exploit pool. Now, you do that for explore pool as well. The prompt slightly changes where you say that, I want look at these points and look at these function values, generate solutions such that they're closer to each other in the next iteration, and my function value reduces. So that's the task of the large language model. It will then generate new solutions, and you can see then in the exploit pool, it has generated points which are way close to each other. And on your explore pool, it has generated solutions that are spread apart, not very close to each other. Right. And this process continues until it finds the optimal solution. Okay, that's how we are enforcing exploration and exploitation. And elitism is already there. All right. Now comes the benchmarking part. Like I mentioned, we had used multiple functions and multiple methods to compare our approach. For instance, scaled sphere, Himmelblau, Rosenbrock sphere, Beal, as well as Goldstein are some of the examples that we have tried. And I've also listed the global minima values. Okay, and we are comparing stochastic gradient descent, Adam, simulated annealing, and all these methods. And in the last column, we are also comparing Leo, which is our method. And you can see this first column with the second, and you can see that we are able to get to the global optimal solution fairly well. Hi, is there a question? Hi, your voice is not very clear. Hello. I'm sorry, is there a question? The user was saying something, but it wasn't very clear.
Oh, sorry. That was extra channel.
Oh, okay. So I can continue?
Yes, thank you.
Sure, thanks. All right. So yeah, the bigger picture that I wanted to bring to you is that Leo performs really well. However, it is not the best. LBFGS as well as CMAES are doing slightly better in terms of the floating point precision. But let me also mention, I may have missed out, these are results of 100 different experiments, not just one experiment. I've repeated the experiments 100 different times, and I'm presenting the median values of all the experiments. So yeah, so these are statistically significant as well. So that gave us some motivation to pursue this approach a little further, and we applied this approach for multiple practical problems of interest. Now, again, this is earlier I showed you the quantitative estimation of how our approach works. And now I'm showing you the qualitative variation, how the solution progresses. You see, it starts somewhere far away from the optimal solutions and gradually progresses towards the optimal solution. So yeah, that was one way for us to show how the solution progresses gradually. All right. Now, coming to the application, the first application that we tested was the nozzle shape design. Basically, what we wanted to do is we wanted to see if a nozzle can be designed with a certain objective using large language model again. Now, what was the objective here? Basically, what we have is a shape which was represented using a cubic Bezier curve with 4 control points. The first and the last control point are fixed because you want the inlet and the outlet radius to be fixed. What you only want is to perturb the control points in between so that you get multiple shapes. And your idea would be then to find the shape such that my flow is parallel at the exit and there is a least amount of radial flow. I do not want any radial flow. So the flow is uniform to the exit. Right. This can be actually done very fairly accurately as well as in cheaply as well using the area Mach number relation in the compressible flow theory. And what we found out is that as the optimization iteration progresses, our function value were reducing drastically, and we were quite surprised to see the rapid convergence in both exploit and explore pool. These are some of the optimal shapes that we initially start with. You see, initially the optimizer assigns random shapes and gradually converges to a bell-curved nozzle, which is what the theory expects. Your nozzle should be bell-shaped. All right. Moving on to the next problem, which is 1D heat transfer. We know 1D heat transfer problem holds a lot of practical relevance, especially to industries. And for those kind of scenarios, we have the governing equation as well. One could use finite difference to then represent that equation or discretize that equation using certain grid points, right? Now, the number of grid points that you choose to discretize your solution, 1D solution with, becomes your input variable. So if I used to represent my 1D grid point using 2 control points, then my number of input is 2. I can increase it to 4, 8, and right. And the idea would be to satisfy the governing equation so that your solutions are physics or are such that it satisfies physics, right? So we compare our solution, that is temperature that is obtained by Leo across the 1D domain when only 2 variables are assigned, and it matches the exact solution really well. I would say at this point in time, it is physics. It adheres to physics as well. However, when you increase the number of variables from 4 to 8, you see the performance degrades. And that has been a challenge with large language model and also with Leo, that it does not do great when number of decision variables increases or we are approaching towards high dimensional problems. But that's a work in progress. We're actually working towards that. Now, moving to the next problem, which is the wind farm layout optimization problem. The target here was to design a wind farm layout optimization such that with the strategic placement of these wind turbines, I get maximum annual energy production, maximum AEP, right? I can use Flores, which is an open source wind farm simulation software, to compute the AEP, and I can use any kind of optimization, right? For that matter, I had used Leo. And to compare our solution with other methods, we are also showing the results obtained by SciPy library. So on the top row, these are the solution that is obtained by Leo when you use 2 wind turbines, 4 wind turbines, and 8. So you see the strategic location emphasizes corners for maximum AEP, and which is also what is the expected solution from SciPy as well. So it was good to note that our approach is able to adhere to the expectations or what we are getting from other approaches. And this is what the convergence says. There is an increase in the power that we get. And this is irrespective of how many wind turbines you get. Right. Now, as I mentioned earlier that, when it came to high dimensional optimization problem, this has been an Achilles heel for us. And to answer the question as to why we are struggling or to probe further, we took the n-dimensional Rosenbrock function, which I described earlier, right? So the Rosenbrock function can be extended to n dimensions as well. Now, if you remember, the global optimal solution for Rosenbrock is at 0. So for all the xi's, which are your decision variables, if they're all equal to 0, you end up at the global optimal solution. Now, you might think at this point of time, this is a very trivial solution for a large language model to get, because an LLM during its training may have seen the number 0 millions of times or n number of times. So it can come up with any arbitrary guess. It can hallucinate towards 0. So to make the problem slightly challenging, what we have done is that we have offset the global optimal solution by a fraction, by introducing this term A, which is some decimal value. Now that becomes a challenge for large language model to solve, because now it can no longer guess a solution, right? So what we tried to do with this strategy is repeat the problem with increasing number of populations, increasing number of, decision variables. And we saw that there is a trend that follows. It does exceedingly well when it came to 2 decision variables, but when you increase it, the convergence becomes much slower. Now, I would like to defend this behavior by also saying that it's a rule that when it comes to increasing number of decision variables, it's a thumb rule that you also should increase your optimization iteration. It's unfair to ask the optimizer that if you're doing well on a 2D problem on 100 iteration, you should also do well, or you should also find me the global optimal solution for 25 dimensional problem using the same optimization iteration, especially if I don't increase the population size. So yeah, that's one of the reason why you see a bad convergence or it not finding the global optimal solution. But yeah, the overarching aim of this exercise was to see the trend and to depict as to what is happening as we extend the problem to larger dimension. Okay, this is the final application that I'm going to show to you, and then we will move on to the reasoning elements. I hope I'm still on time. Right, so as I had mentioned, for multi-objective optimization, things are slightly different. So far, we have seen how large language model works for single objective optimization. But what happens when we are dealing with multiple objectives or multiple conflicting objectives? Well, to test that, we chose these popular problems, ZDT1 and ZDT3. You can see the function values are given by this expression here, F1 and F2. And you can use this expression to compute your objective function values. The idea would be to ask the large language model to give you the Pareto optimal front, like I mentioned. For multi-objective optimization, if you're dealing with conflicting objectives, you're going to get a Pareto optimal front. So to get the ground truth solution, what we did is we took the original NSGA2 framework by PyMo, and we took an exceedingly large number of population or solutions and ran it for exceedingly long amount of time so that we know for sure that those are your real solution, those are your global optimal solution. And we have done it for both ZDT1 and ZDT3. So now we compare our solution, that is NSGA, Leo modular with NSGA2. Now, how Leo modular works is, if you look at this flow chart, which is the description of NSGA2, I basically remove the crossover and mutation, which are essentially ways of perturbing the solution or generating the solution using large language model. That's the only change. I have not changing anything else. So that is what Leo modular is. So it should still give me solution, right? And then we see that at the end of n optimization cycles or iteration, our solutions does compare really well. In fact, quite good compared to the ground truth NSGA2 solution. And this is also true for ZDT3, where you see the Pareto optimal front is fragmented, and it became really crucial that we should target these kind of problems and see how well it performs. Okay, so that was the final application. Now let me come to the reasoning part. If you remember, I mentioned something that is part of this framework, which is elitism. That is, we take the best solution from explore pool and we take it to the exploit pool. Sorry for the confusing words. We take best solution from explore and send it to exploit. Now you may ask at this point in time, that in some sense is some kind of a filtering. If you do it long enough, you are bound to get some kind of an optimal solution only by the virtue of that. Now, that is a fair question to ask. So what we have done is we have devised ourselves another framework, which is Leo R&D, and which is something that generates solution, but without context and without any guardrails, right? And we compare that with Leo. So the idea would be, can we take a Leo-like framework, but not provide it any context and not give it the guardrails? Will it perform still as good as it did? Now, that would attribute to the reasoning, right? So this is what we try, and this is actually the entire prompt, if you can see. For the explore prompt, what we are prompting is, well, with these limits of min-max values of each variable, you must provide exactly 10 new but completely different and scattered set of values to explore away regions for minimizing the function values and generate the result like a CSV file with 10 rows and 2 columns. All right, so that the data parsing becomes easier. Now, this is for explore, and you can guess what will happen in exploit. We will say the opposite. To exploit close by regions, that's the exploit region. Explore. Now, but if you note, for Leo R&D, we do not say anything like that. We will just feed it the input values, and we will say, give me a new set of points. All right. Now, this is where the difference comes in. Leo versus Leo R&D. And if you note, Leo converges much, much faster, whereas Leo R&D takes a significantly longer amount of time. I would say that it plateaus and does not really converge. And this is both for exploit pool as well as explore pool. On the other hand, if you compare the density plots, this is something interesting we observed. If you see the density plot of the solutions from Leo, especially, you can see that in the from different iterations, as in when we are progressing from 0th iteration to nth, the final iteration, the density plots moves closer and closer to the optimal solution. This not only happens for exploit pool, but also explore pool. This is really surprising because there is reason to believe why this convergence will happen for exploit, because you are converging towards a space. But you remember, explore pool does not have any such precedence. There was no need for it to converge towards the reason, but it still did that. And then, that was something that took us by surprise. Right, but you will not get that kind of a convergence using Leo R&D. As you can see, for the 25th iteration, we are going apart. All right, I hope that gave you some clarity towards the reasoning element of large language model for optimization. This has, like I mentioned, been a curiosity-driven investigation that we wanted to embark on. And we had certain problems that we wanted to try. So yeah, this is what we ended up doing and publishing as well. I wouldn't go out to say that this is a foolproof method. There needs to be a lot of work that needs to be done to make it much faster in terms of function calling is concerned. Then maybe we can compare. That's when the actual comparison happens, right? But yeah, as far as the theoretical value is concerned, there is a lot of promise. So yes, that's my presentation for today. I would be really happy to take your questions and beyond this presentation as well. If you have any questions, feel free to reach out to me or my manager. Thank you so much for your time.
There's a question up front.
Yeah, I've got a number of questions. Can you hear me?
Yes, I can hear.
Well, the first is when you were going down the path of looking at like DeepMind's work, did
Yes.
you go any deeper into like particularly like AlphaFold and again, I don't know the specifics of your engineering problems, but AlphaFold or the sort of neurosymbolic examples. And I was wondering if how far you went down that path before you went back to sort of a gradient free. I have a couple more that sort of choices you've made about the models, choices you've made about even using LLMs in the first place, but maybe that first one works.
Right. Thanks for the question. Well, no, we did not explore the method that are used in AlphaFold, to be very frank. Although we are slightly aware of the strategy that they have been used. But yeah, our approach was to completely take the route of gradient-free optimization, given that we have, for these problems, we have faced certain challenges with gradient-based optimization, and we wanted to see if large language model would provide any merit.
I think my second set of questions, which is, it doesn't really seem like a gradient-free approach because you're using the sort of foundational models as a loop of reasoning in and out, and it looked like the guardrails were really sort of your gradient-free decision making. Part A question was why not train your own model? But B, like I guess now I would look at like reasoning models and agentic solutions around this.
Well, to answer your first question, yes, to some extent you could say that, but I would still say that there is no time history of solution that is given to the large language model as context. So from one cycle to the next, that's the only context it has. But beyond that, it does not know what the solution, whatever it saw. So the gradient of time, gradient with respect to time is not available to it. So I'm not very sure. So that's the answer to the first question. As far as the second question is concerned, yes, again, you could definitely train a neural network for such problems. Although I believe the limitation might be it will become probably problem dependent. And we saw that with slight change of prompts, it worked really well between single objective to multi-objective. Whereas I'm definitely sure that when it came to training a model, you need to have a different paradigm for single and multi-objective optimization. That's my opinion here.
Great presentation. Yeah, I have a few questions. This is
Yes.
first of all, really, really cool. All right. If we can turn back to slide 24, I have some questions with
Yes.
I think it's so when we look at evolutionary computation, right? One of the
Yes.
things is hybridization, right? So you can have an integrated hybrid or interdigitized hybrid, yeah. And so you're, you know, in your other when you were looking at a single optimization problems, you were like, well, okay, it did pretty good, but it lost to some of these other methods, right? So
Yes.
have you thought or looked into hybridization with some of these other techniques? Because the LLM will be able to mimic them. Okay, so that's the first question. The second question, when we look at NSGA, I have not seen, and we have a whole bunch of multi-objective evolutionary optimization techniques, right? I have not seen much of any work on hybridizing, right, NSGA too. What you
Okay.
have is a really nice way of doing that with an LLM. So the thing is, what you did is you went, and it's also interesting that you did exploitation before, and well, and I can see why you would do exploitation before exploration. But underneath exploration, you can kind of put anything else you want, right? Okay, because you're starting, you know, very wide, then you got your exploration, and then you can kind of, you know, you can tack on any kind of other gradient descent, you know, to see if you can lift up and then move back to that Pareto. So I just spent, I'm excited, okay, and I just talked a lot about, have you done anything with hybridizing, this approach?
Right. Thanks for your questions again. So as far as hybridization is concerned, I'm not very sure if I get it entirely correct because I'm not that familiar with that terminology. Could you please tell me what do you mean?
Okay, so what in evolutionary computation, what some people will do is they'll go ahead and turn on the evolutionary computation until it converges, right? So these you know, ECs are really good at identifying promising regions in a certain. Okay, so once you identify those promising regions, then you go get a gradient-based method to drill down.
Right, right, yes, yes.
Now, if you don't have any selection or replacement, you know, the thing is that this algorithm, with what the way you're using exploitation, right, and elitism, it gives you a little bit of a killer instinct, but you know, if I'm using elitism and I get a population that's kind of converged in terms of fitness, right? Then your elitism goes bye-bye, right? Because what you're doing is you're selecting or potentially can select individuals that have the same fitness, but their genetic diversity is wide ranging. So you never move in one direction. You just slide kind of across the that neuron.
I see, yeah. Again, an excellent point you bring out there. So yes, I'm familiar with that context of, or that angle of hybridization, where you start with a population-based approach, given that it is going to give you fairly good solutions close to the optimal solution, and then you pass on to the gradient-based optimization to further drill down onto your global optimal solution. So that is something we haven't tried, but I've done that in the past with other approaches. during my PhD, but not with large language models. And I can see the parallels there. So yeah, that would be something that one could indeed do. And yes, as far as your second question is concerned, we haven't sort of applying any kind of hybridization for this problems. To our surprise, this Leo worked really well for multi-objective optimization, even better than it did for single objective. So the focus was unfortunately slightly less, but I'm sure if we had more time, we would have sought for a much more or a better hybrid approach. But yeah, since it performed rather well, we didn't think of drilling down further. I hope it answered your question, but I'm happy to get back to you.
Are there any other questions? All right, if
Oh.
not, thank you so
do we-
much. Really.
Okay.
Thank you.
Okay. Well, thanks, everyone. And did you have another quick query?